Welcome back to Salts of the Earth, an 8-part video series on issues related to salt attack in adobe and earthen structures. My name is Eric Liefeld, and I'm with Mesilla Valley Preservation. In this video, we'll delve into the basics of how salt attack works and show examples to help you recognize it. Salt attack and rising damp are terms that sometimes get used interchangeably. In actuality, these are related but distinct processes. Because people typically worry about moisture in adobe, capillary action is a popular topic. However, moisture alone simply cannot explain the masonry damage that we frequently see. There is often another more destructive side to this process, driven by repeatedly dissolving and crystallizing salts. This slide illustrates the vicious cycle that combines the two. Here we have a cross-section of an adobe or other masonry or earthen wall. Recurring moisture is falling from a canale or drain spout and soaking into the ground. The surrounding soils contain salts that are dissolved as the ground becomes saturated. Because this saturated soil is against a porous masonry structure, capillary action within the pore structure of the wall draws or wicks the moisture upward. This, then, is rising damp. The moisture rising within the wall eventually finds a way to evaporate through the lattice of pores, usually at or near the wall surface. The dotted yellow line denotes an evaporative or drying front. The position of that front can vary as a function of both the porosity of the wall material and relative humidity. As evaporation occurs, the dissolved salts crystallize. Initially, this takes place within the pores of the adobe, as the crystals are quite small. But over time, as more salt-laden moisture is drawn to the wall base, the salt crystals grow larger and larger, to the point where they literally outgrow the pore structure of the adobe. Remember, this is occurring on a microscopic level. The important thing to understand is that these growing salt crystals are able to exert truly enormous crystallization pressures on the walls of the pores where they reside. Eventually, the adobe, or brick, or stone, or concrete begins to crumble off the wall surface. Over time, a cove develops as the wall is undermined. The salts and destroyed adobe form a little telltale pile of powder in the base of the cove. The fallen salts then dissolve with the next wet cycle and are returned into the wall base. So you can see that this is a vicious cycle. It literally only gets worse with time as salts continue to concentrate. The salt concentration only rises. If there is one thing to take away from this slide, it is that evaporation is just as important, if not more important, to this cycle than the moisture itself. Moisture is certainly an issue, but it is aridity and evaporation that is the driving force for the damage we see. I want to emphasize that salt attack is actually a very well-known problem, especially in concrete circles. The concrete industry has understood this process for a while. Here is a description quoted from an American Concrete Institute presentation that describes in lots of words the process that we just looked at graphically. Note that in this case they are talking about the destruction of concrete. The last point here is very important. Once the salts are present, they literally are capable of driving this process on their own, creating a microscopic freeze-thaw cycle that can literally take place multiple times per day. We'll talk more about that later. In order for salt attack to happen, a number of things have to be in place simultaneously. Alkaline soils, porous building materials, an arid climate, repeat wet-dry cycles to cause salts to concentrate, and time. Alkaline soils are high in salts. As this U.S. Bureau of Reclamation map shows, alkaline soils are particularly common in the American West. Shaded areas represent different levels of salinity. Black areas, such as the Mesilla Valley, are labeled salinity by irrigation. Flood irrigation in particular increases salinity, concentrating salts in the upper layers of the soil. Porous masonry is also necessary for salt attack to occur. It is very important to remember that this is not just an adobe problem. All porous masonry is subject to salt attack, including brick, stone, and concrete. Again, the concrete industry is very aware of these problems. In fact, this illustration came from a concrete industry presentation. Although it is counterintuitive, an arid climate is a real driver of salt attack, because dry air drives rapid evaporation that concentrates salts. Salt attack can't exist without evaporation. Of course, the arid West is only becoming more arid these days, as are other parts of the country and world. Salts have interesting and insidious properties that pertain directly to the damage they cause in salt attack. First, salts are water-soluble. Salts are also hygroscopic, in that they attract water to themselves. They will even attract moisture directly out of the air. Salts are also deliquescent. This means that once salts attract moisture to themselves, they literally dissolve themselves in that moisture. As the moisture evaporates again with the next dry cycle, the salts are capable of generating massive crystallization pressures. It may seem odd that these crystallization pressures could do damage, but the numbers are impressive. For example, the crystallization pressure for sodium chloride, or table salt, or halite, is 56 megapascals, which translates to over 8,122 pounds per square inch. That's over 4 tons per square inch. In contrast, adobe has a very small tensile strength. I found one source that put it at 0.1 megapascal. So there is simply no contest here. In fact, no masonry material can really resist these forces, not brick, stone, or concrete, and certainly not adobe. This slide shows a couple examples of deliquescence in action. Areas that have a high salt concentration are clearly visible as they appear dark because they are actually wet. In this case, they are not wet from rising moisture or capillary action. They appear wet because the crystalline salts have extracted moisture from the air on a day with high relative humidity. The salts have attracted moisture out of the air and dissolved themselves in it. So yes, moisture can bring salts. Likewise, salts can also bring moisture. Salt deposition can take place in at least 2 distinct forms. Most people are familiar with efflorescence, as shown on the left. With efflorescence, salt crystals grow on the surface of the wall. Though this can cause cosmetic issues, it is generally preferable to subfluorescence, which we see on the right. Subfluorescence is the more damaging form of salt deposition. With subfluorescence, salt crystals form in the microscopic pores of the masonry, adobe in this case. Here we see the characteristic finely powdered adobe that results as the wall is steadily blown apart on a microscopic level by crystallizing salts. Importantly, with subfluorescence, the microscopic salt crystals are typically completely invisible. On rare instances, they can be seen with an optical microscope. Just because you don't see salt crystals doesn't mean they aren't there, and it doesn't mean that you don't have salt attack. Though they are elusive, we have been able to isolate crystals from subfluorescence using optical microscopy. You can see that they do not resemble the cubic salt crystals that salts form in the open air. Instead, these crystals resemble transparent glass tree roots, taking the form of the microscopic pore structures in the adobe masonry where they grew. Here is the same salt crystal when viewed by an electron microscope. Notice the root-like structure and the little structures that look like stalagmites. As described by the scientific literature, as the crystal grows, the larger portion of the crystal draws moisture toward it. That salt-laden moisture then contributes to the growth at the large end of the crystal. The crystal eventually exerts enormous crystallization pressures on the wall of the microscopic pore system, and ultimately fractures the adobe. It is useful to be able to identify the exact salts that you are dealing with, as different salts have different properties. The electron microscope can also be handy for actually identifying the substance we're looking at. By using energy dispersive X-ray spectroscopy, the electron beam is pointed at the sample, and an X-ray detector can then classify the spectra coming off. The spectra on this slide is impossible to read at this size, but what it shows are 2 very distinct spikes for sodium and chlorine. So in all likelihood, the crystal we are looking at here is sodium chloride, or regular table salt. Your salts may differ. Next, we'll examine what salt attack looks like. Once you know what to look for, salt attack is painfully obvious to recognize. This 150-year-old adobe building in Mesilla, New Mexico, is exhibiting the characteristic coving of salt attack. On the exterior, the salts have climbed above a concrete collar that was added at some point to combat the problem. On the interior, we see failing attempts to repair very serious salt attack damage, with rocks, bricks, and cinder blocks. Here is some even more dramatic salt attack on an adobe building in Las Cruces, New Mexico. Note how the salts have completely undermined the wall and turned the adobe into a fine powder. This adobe wall in Mesilla has had a concrete collar installed to try to deal with the damage. It has subsequently been plastered with Portland cement-based stucco, and painted or coated sometime after that. Despite these efforts, salts are actively damaging the surface of the wall, and are likely wreaking more havoc within the wall. As we've said, salt attack is by no means limited to adobe. This is a relatively modern slump block wall that is laid up with cement mortar. the wall is undergoing significant staining and damage from salt attack. Even relatively hard materials like cinder block and concrete can't resist the extremely large forces that crystallizing salts can apply. Salts have rendered the lower course of cinder block almost unrecognizable and caused the surface of the concrete to flake off. This is a brick building on a concrete foundation, built around 1910. The building owners have had it plastered with an elastomeric coating. Here we see that the salts are rising through the concrete foundation and destroying the brick and mortar behind the elastomeric coating. The result is the appearance of blistering that we see fairly often, as the powdered brick and mortar accumulate behind the elastomeric coating. Here we can see how rapidly salt attack can progress, as the exposed adobe wall had gone from being undermined, partially collapsing in only a year's time. We can also see moisture and salts climbing over ineffective concrete patches on the far right of the image. Finally, here is a situation we often refer to as structural plaster, because plaster is sometimes seemingly the only thing holding up the wall. As you can see, despite layers of Portland cement plaster and a later concrete collar, much of the load-bearing adobe wall has simply ceased to exist. All that is left behind is the powdered adobe and the endlessly circulating salts. This 150-year-old adobe building was demolished a few weeks after these photographs were taken. Thank you for joining us, and I hope this video has helped you to understand and visualize salt attack. Other videos in this series focus on how to accurately detect, measure, and remediate salt attack in adobe and earthen structures. Please subscribe to our YouTube channel and enjoy the rest of the videos in MVP's Salts of the Earth series.